great to be here. I know you probably want to hear more of Mo's talk, and there's nothing I can do about it. So it's all downhill from here. My name is Damian Roqueiro. I work for Roche at the moment. Before I was at ETH. And let me just try this. Yeah. And this slide is just to show you a snapshot of what neuroscience and rare diseases is at Roche. We are based in Basel. And what I'm mostly interested in showing you here is this list of focus areas of research in NRD. And as you can imagine, in order to tackle all of these different conditions, there has to be a plurality of labs in the company that obtain data from different models, organobiology, human genetics, protein synthesis, and additionally, animal experiments. And the focus of today's talk is to show you what does Roche do with animal experiments and how to better analyze that data. In particular, I'm going to focus on Huntington's disease, but the model I want to show you today can generalize to any disease. All right. So to find mechanistic answers to questions about neurodegenerative diseases, it is important to understand disease progression. This cannot be stressed enough. In animal models, the researcher wants to contrast two things. First, the trajectory of a given phenotype as a healthy animal grows old versus the deviation that occurs due to the onset and progression of a neurodegenerative disease. So trying to identify as early as possible the point where the two diverge is essential for the development of new treatments and testing different compounds with the goal of trying to see if we can bring the diseased animal as close to the control one. Apologize. OK. So in the animal experimentation in biomedical research, being in academia or in industry, people must adhere to the highest standards. In Europe, in particular, there is legislation that aims to enforce the so-called 3 Rs: reduce, refine, and replace. The focus of today is the reduce part. And as you probably know, researchers nowadays are benefiting from an abundant number of software tools, and as you can see here, technological equipment, to essentially extract more from their animal experiments. Many of you are probably familiar with tools like Deep Lab Cat, where you can essentially track any body part of an animal with minimal effort. So I just want to show you here quickly 2 different models that we are using. The one on the left has a camera and a cage that houses different animals. Here in plural, we're going to have 3. Each of them is identified by an RFID chip. And the one on the right is a general rack where we have different cages for individual animals, all of them fitted with panels at the bottom that can get sub-centimeter resolution of where the animal is located in a non-invasive way. This is just a snapshot of the one I just showed you earlier, so the one here on the left. What the camera captures is what you see there. And one can go 2 ways. Have a person annotate every single behavior of interest in these very long videos, and that is, of course, time-consuming. So my colleague at Roche, Yan-Ping, she developed a machine learning model where, with minimal training, we are able to actually identify specific behaviors. These are called bar climbing, vertical climbing, rearing, or simply distance traveled, which we can identify through the RFID. Remember, each animal has one, so the animals can be disambiguated. This is what the data looks like. So the way the experiments are conducted, recordings take place in blocks of 3 consecutive days. They all start at week 8. And they are repeated every 4 weeks up to week 32. So I'm showing you here just one of these 3-day blocks. And you see the activity of the 3 animals. Three key things to show you. Number one is that, as you know, mice are nocturnal, so their period of activity is actually when the lights are off. Nevertheless, when they're supposed to be resting, there is some synchronicity of activity. Perhaps when one of them wakes up, disturbs the other ones. That's marked in number one. Then number two shows you what is called an anticipation. So the animals know when the lights are going to be off and become active, and they become active before that. And then there's a small siesta period marked with number three. And the data looks like something like this. There's some additional preprocessing, binning of the data in 10-minute bins, but you can get a data set tidy as this one. And normally the next step is to perform what is called a traditional analysis. And in this traditional analysis, and by that I mean the ones you actually see in publications that are trying to show the efficacy of different compounds, what people do, and I apologize for the colors, I'm not sure why they turn out like this, but what people do is essentially slice the data in order to be able to conduct statistical tests. So imagine you say, okay, I just want to see if there's any effect between my two groups, for example, the wild-type animals, and here the knock-ins are these Huntington's mice that have a mutated version of the Huntington's gene. And we do it 1 week at a time. We conduct the test, we correct from multiple hypothesis testing, and we get something like this. Now, from here, you can imagine we're missing a lot of information, in particular those nuances that I mentioned earlier about what happens in between of certain periods of activity and the relationship between the animals. Not to mention the fact that we have to assume that all the data here is independent, and many of those assumptions actually don't hold. So having said that, then I want to show you what we decided to do in order to overcome these limitations of the classical models. And we decided to use what is called a Bayesian model with a hierarchical structure. Under the hood, we have Gaussian processes, all of them combined using a general additive model. Now, in this type of model, each feature F, so here a feature is actually an activity, bar climbing, distance walked, etc. Each of these features for a subject I at time t is assumed to be normally distributed. And our goal is to learn from the data the mean of this distribution pi. Now, what we are imposing on the model is this structure where we say that the activity of the mice in the same cage is going to have an influence on the mean that we compute of the activity for that cage. Similarly, the means that we have at the child level here for the different cages are going to have an impact on the mean that we infer for the entire wild-type group. So I'm sure everybody is familiar with Gaussian processes, but just to give you a quick idea of what we are after, especially because I wanted to contrast it with what I mentioned earlier about getting an average of all the data and doing a statistical test for a specific week. Here, what we want to do is we want to use our data to learn a distribution of the values and also learn some of the uncertainty. Again, I apologize for it not showing here, but what you normally do is the more points we get, then we diminish the uncertainty around those points. Now, the Gaussian processes in our hierarchical model give us a lot of flexibility in this respect, and that's exactly why we went for them. So with fitting the model, let me show you here the results for two of the selected features. One of them is called bar climbing. The other one is the RFID, remember the distance walked. And the first thing to notice is that we can see that the predictions of the model actually are in accordance to the real data. And that's a good thing. One key aspect of the model, especially shown here for bar climbing, is that we see for orange, which in this case is the knocking group, that there is extra activity at the beginning of the lights off period. And this is also a staple of Huntington's disease. So there's a period of hyperactivity when humans, and in this case also animals, come out of a rest period, for example, from sleep. And this is important that we can also recognize it here. Now, on the right-hand side, we see the expected activity for both groups relative to the first week of the wild type. I know it's probably hard to follow, but the idea is essentially to show that the model actually learns a decay of activity. First of all, for the healthy animals, it makes sense that they are less active simply because they are getting old. And for the diseased ones, then we expect an even more increased or decreased amount of activity. Okay, and one question we want to answer is, on average, what is the difference in activity between the two groups in a given block? And the plot on the left is showing you the median of the effect size when we compare the knock-ins versus the wild type. Again, we also see how this recapitulates what I mentioned earlier about this period of hyperactivity. And another thing that we also see is that this, here for bar climbing, the animals are more active, and we see that this is present when they're young, but as the disease progresses, then we don't see that. In fact, we see that a negative effect, meaning the healthy animals are more active than the diseased ones. Now, on the right-hand side, there's another interesting aspect of this model that goes beyond of what a classical method, a linear mixed model, can offer us. And it's this idea of what is called the probability of practical equivalence. So in a way, you can query the model, and you can ask, can you give me the probability that in a specific bin or a specific time period, the activity or the amount of the activity for the knocking group is larger than the amount of the activity of the wild-type group, plus a number of seconds. And here, this is showing you for 1 second, but the truth is that this is a parameter that one can use. It has to be relevant to the disease that we are analyzing or to the compound that we are testing. And it's another important aspect of the model because we're using the posterior probability to actually infer these values and have a quantification, if you might, of what I mentioned earlier, that one can say, well, they are more hyperactive. Well, here we have a probability measure for that. So in the interest of time, I'll go quickly over this one. This is just to show you that we attempted to do a type of cross-validation. This is different, of course, from what you will do in a classical machine learning approach, where you have a point estimation. Here we have a probability distribution. This is what is highlighted here with the empirical cumulative distribution. There is a very interesting paper from Roqueiro et al. That essentially tries to put together the way in which one can take an empirical cumulative distribution function and obtain a single score called the continuous ranked probability score. And in this case, what we did is we trained the model on all the data, then we took out a cage, and we see what the difference was for the ECDF CRPS score. And as you can see here, the values are in accordance to the other ones. This is when we exclude cage 5. Alarms will go off if, for example, this value is quite large compared to the other ones, but in this case, the model seems to be behaving well. And finally, this is just to evaluate the robustness of the model. And another goal for the project was, in addition to be able to model this activity, can we use this ability to query the model to essentially ask questions and say, what if instead of using 8 animals, we use 4? Will we still see the same effect? And that's important, especially for animal experiments. As you can imagine, the less animals that are being used, the less burden that is for the experimenters and for the company. So what we tried to do here was to blind ourselves to settings where we assume that, for example, instead of having data for all weeks, we only have data for 4 of them, always trying to keep the time in between weeks constant. And one of the things we see here is that that doesn't seem to have an effect. So here we have what is called the relative effect size, meaning that when we compute the effect size of the model with the totality of the data, all the other points, that's just why you see one, all of them overlap. No problem here. Now here we see that there is a problem, or something to take into consideration. And that is the fact that if we start removing cages, then the model cannot learn properly the effect. And one thing to note here is that of the 9 cages that we had, 5 were for control animals, 4 were for the Huntington's disease model. And as you can see here, the moment we start extracting cages and trying to make sure that they were balanced, then the expected effect size varies. All right, so to conclude, in neurodegenerative diseases, as I mentioned earlier, the key is to understand disease progression. And I try to convince you that statistical approaches do not take into account the factors, for example, like the temporal correlation. As I said, one can use standard linear mix models to say, well, animals come from the same cage, or this data comes from the same week, and by adding these covariates, we can try to regress those factors out. But the interactions between the animals are poorly understood if we follow that path. And in our case, the Bayesian model that we propose is using the concept of a hierarchical structure. So in this case, we are trying to model the fixed and what we call also random effects. And the estimation of the effect size, so contrast this to, for example, to the standard, kappa, Cohen kappa values when you try to do normal effect size estimation. Here it's called the average treatment effect. And we try to quantify specific differences between the group. One of the key things I want to highlight here, you probably saw their faces in different slices, especially when everybody contributed to the specific project. This project was also a good example of how a company like Roche was able to collaborate with another company like PyMC Labs. If they are not in your radar, I recommend go visit their webpage, especially if you're interested in Bayesian inference. They're doing fantastic work. Now, the package will be available soon. We're finishing the preprint. And so stay tuned or contact me by email, and we will give you early access to it. And then the last thing, just to acknowledge all the work that was done. There's a huge amount of people that participated in this project. I want to highlight Owen O'Connor. He's the lab head of the In Vivo Technologies Lab, the one who designed the experiment, the one who conducted them, the one who had the vision to actually create this model. Harry, she's the one that worked on what is called a RISE program. So she was a PhD student at the time, and she spearheaded all this project. And Roger Redondo is the head of the Systems Neuroscience section, where I was at the time when we did this project. And here you have these guys from PyMC. In fact, I want to highlight Thomas Vicky. As I said, if you visit their webpage, you're going to see lots of interesting coding projects. But Thomas, in particular, is a very avid blogger, and he attends many conferences. You can find him in YouTube, especially if you're interested, again, in Bayesian inferencing. Having said that, I thank you very much for your attention. It was great to be here, and if there are any questions, I hope I can answer them.